Andreas Zeller. I'm the author of the Debugging book, and I'm here to present you a new chapter. Hello, everyone. Great to see you again. Okay, ladies and gentlemen, great to see all of you again, back again in a new instantiation of automated debugging. Question, we have Konstantin on board. Konstantin, can you hear me all right?
I can hear you, though I have some constant noise in the background. I don't know whether it's my problem or the problem of your microphone.
Problem of my microphone, who knows? Yeah, I can also change to another microphone. Let me just check that just for a second. So switching over to another microphone as we speak. Is that better now?
That's much better.
Yeah, but you have, but I can hear, but now it's more difficult for me to hear you. How's that?
Well, I think it's fine.
Okay, so if it's better for you, we'll stay with that we're going to stay with that microphone then, okay? Let me just see whether we have anything in the chat window regarding bad audio quality. We had that last week. Nobody says anything in the chat window. Okay, good. So before we start with our topic for today, which is mining function specifications, and another magical technique of automated debugging. Before we start with that today, first a small announcement. We have the grades ready for the first project. Konstantin, any comments on that?
Yes, so the grades are in the system. I just need to tick one box and push Save Changes button to release them.
Okay.
Yeah, let me check whether everything is all right. But yeah, either right now or maybe after the lecture, so that our students are not
distracted
by the news. Yeah.
Okay, we'll do this right after the lecture. You have to wait a moment, but I'll try to keep the lecture as short as I can, such that you can immediately jump on your grades. And Konstantin, we also have news regarding the third project.
Right, so we are ready to release the third project. The deadline for this project will be the 5th of February. And well, again, we will make it available right after the lecture, and also we post in use and make a proper link to this.
Okay, so today after the lecture, you're going to get 3 news. One is regarding the new chapter that we're looking at. One will be regarding the grades for the first project, and one will be the third project, which we'll be looking at. Okay, if you have any questions, feel free to raise your hand or ask something in the chat window. Konstantin is going to monitor the chat window and will tell me, and Konstantin can also raise his hand. We'll be around. Okay, no questions at this point. Then let me get to you, as promised, to a new chapter in automated debugging. The chapter we're going to look into this week is called Mining Function Specifications. And before you ask, what does this mean, mining function specifications, I will illustrate this right away with an example. Let me share my screen here and let's see whether things work. So which screen are we sharing today? Desktop 1, desktop 2, desktop 3. And miracle, here we go. You should now be able to see a nice screen with the Jupyter Lab and stating mining function specifications. Konstantin, can you confirm?
Yes, all right.
Wonderful. Konstantin has a really bad internet connection, so I can always assume that if it works for him, it's also going to work for everybody else, which may be a gross overgeneralization, but I digress. Let's go right into our chapter right now. Topic today is mining function specification. And you wonder, why would I mine a function specification if normally the normal way of things would be I first specify what a function should do and then I implement it. Well, folks, sad reality is, in all generality, function specifications hardly ever exist most functions are written by programmers who don't take the time to actually document things, who don't take their time to actually document any assumption they have about their functions, who don't care to document any constraint on the inputs or the outputs of the function, no formal preconditions, no formal postconditions, no nothing, just plain code. This is the sad reality. And this is actually why techniques such as introducing assertions to a piece of code can be so super effective, because in most cases they are not even there. Now, the problem is that actually writing these specifications can be a bit of a pain. And a typical example for this is Python. Python is a language in which typing exists, but typing is being done dynamically, which means that types are checked only at runtime. If types don't work at runtime, then you're going to get a runtime error, but there is no static checking of types as you might know it from the compilation stages of a C program, a Java program, or an ML or Haskell program. So all languages with strong static typing, nothing of that kind in Python, which makes writing Python programs a breeze because you can just write things down without ever thinking about types, but which also makes it more and more difficult to maintain them after some time. I'm going to look into let's look into a very simple example here. We're having a function sum2, a plus b, there we go, and this returns the sum of a and b, but there is nothing that tells us which would actually be the arguments be of this function, so I can put into integers here, and oops, sorry, what have I done? Oh, sorry, it's called sum2, not sum, what am I saying? So here we go, sum2 gives the sum of two integers, but I can also pass into floats. Well, converting integers into floats and possibly vice versa is a built-in feature of many languages, so nothing to worry about. But I can also come up and say, I want to build the sum of two strings in here, auto method, and say debugging, here we go. And then the whole thing nicely returns the sum of two strings. Actually, anything that is compatible here, anything which you can apply a plus operator on will be valid. With this, of course, is a recipe for, well, it's a recipe for lots of flexibility while writing things. But it's on the other hand, it's also a recipe for trouble, because if you don't specify what the expected types of these functions are supposed to be, and if you don't check them at some point, then at any point, some other programmer using your code can start misusing your code, putting in other types, putting in whatever is compatible with the implementation. But then you want to change the implementation, and then all of a sudden, because programmers were programming against your implementation rather than some specification, all of your code suddenly breaks. So you cannot change your code anymore, which is bad, or every change breaks things. It would be much better if you would actually say, okay, I'm actually having a type declaration here, and I'm saying, well, a and b are supposed to be integers, and the whole thing actually returns an integer, such as this. And lo and behold, Python actually supports such annotations. It just doesn't check them at all. Well, or let's put it another way, it leaves it up to the programmer to actually check these. And there's packages in Python. There's the enforce package, which allows us to do this dynamically. And there is also the MyPy static checker, which takes the code of a Python program and does static checking on it, and actually then finds out that a call like this, which puts in strings, whereas actually here integers would be expected, then you're going to get an error both in the runtime checker as well as in the static checker. Now, a problem, however, is that Python programmers, and I'm no exception to that, actually don't like putting in types because, well, isn't it obvious what the types are anyway? I had a discussion with my PhD students some 2 years ago where I asked, Should I put types into my Python code? Yes or no? I'm sure you're all going to say yes, and then I'm going to put them in. And my PhD students unanimously said, no, don't put types. It's only going to be distracting, and it's going to be less readable. And I was very surprised at that, but that's how it is. And this is why the debugging book and also the earlier fuzzing book don't have any type annotations. Okay, I'll be happy to hear your comments about that, since it's not always, since you are the ones who have to understand all this code. Would it be better if you actually had type annotations? The world is open. Okay, but fortunately for us, there is a way to actually get those type annotations back, and not only get those type annotations back, but actually also get pre and post conditions for existing code right out of an existing execution. And let me just show you how this works first, or how this is being used first. And then we go into details on how this actually works in the background. So the idea is as follows. We're having a nice little package which is called dynamic invariance. And this dynamic invariance provides us a class which is called a type annotator. Type annotator, okay, here we go. From dynamic invariance import type. When is it underlined? Oh, this is underlined because I haven't used it yet. Okay, and now I can say with type annotator, you'll see we're always using the same idioms here. It's always some type thing, or some with thing. And I'm using this as annotator. Here we go. And now the way I'm using this type annotator is I'm using this with actual calls, such as this one, for instance, 1 + 2. So, and what this type annotator provides is it provides a representation of the program that is compatible with all the executions we have seen so far. And the way this works is as follows. I can do this right away in here. We can do print, and then I use the annotator dot typed functions. Here we go. And this automatically prints out a version of the functions that we have observed, and now with type annotations. So all I have to do at this point is I can go and replace my original definition with what I see here. For instance, I could go and copy paste this thingy here and put it in here, and now I have a typed version of sum2. So if you have trouble finding that Python code is not typed enough, there's ways to do that. So how does this typed annotator actually do this? Well, it's very simple. We have seen in this course how to actually track individual function calls and how to track individual arguments to these calls. And what the type annotator does is something very simple. It simply records for every function call that it sees, it simply records the types of every single argument there is. So in this case, we are invoking sum2 with 1 and 2. Both are integers, and therefore it learns that A must be an integer and B must be an integer too. What happens if I invoke this with 2 real numbers? So let's make a new annotator, and now we're invoking this with real numbers. Well, you won't believe it, and then it tells us that A and B are of type float. And if it turns out that we put in 2 strings here, for instance, 1 and 2, something like that, then it's going to luckily show that A and B are both strings, and that the return value, which it actually also tracks, has a type of string. Now we can have some fun. We can also go and invoke this multiple times. Say, what happens if I invoke it first with, I haven't tried that before. So what happens if I invoke it first with integers and then with a double number? Then it's going to tell us, oh, apparently you can invoke sum2 with any type, and there's a special any type which matches anything, and the return value too is actually anything. So how does this work? And this is something you can look up in the book chapter. It actually works by tracking all these calls and by tracking all the types of all arguments. And interestingly enough, should you have a large body of code that is written in Python without any type checking, you can actually use this type annotator and run your existing code on it. And then it will provide you with actually type annotations for every single function and every single argument. Not so sure whether it also works for keyword arguments. That's something to discover. But it certainly should be able to provide you with all you need for positional arguments. So that's a simple thing already, and this gives us the key idea of this chapter, namely looking at actual executions, and from what happens in these actual executions, abstract into a generalization which actually holds for all current runs and possibly also for all future runs. So type annotator is something convenient, which is definitely for an untyped language like Python. But we can also get a bit further, a bit deeper into the possibilities here. And the second thing we're looking into today is another class which is called Invariant Annotator. Then you wonder, what on earth is an invariant annotator? An invariant annotator, ladies and gentlemen, provides us with not only with types, but actually with a number of properties that hold for all runs observed. And I'm going to illustrate that on with a number of calls on sum2. So let's make that 0 and why not 0? There we go. And what does the invariant annotator give us? The invariant annotator does not provide us a method type functions, but instead it gives us a method functions with invariants. Oops, invariants. There we go. Let's see. And these invariants actually provide you with information on properties of the individual values. And I'm just slightly confused because this should give you a bit more than that. 1 second. Why is that the case? No, sorry. What's happening? There's something wrong in here. I don't know exactly what's wrong. That's what happens. Minus 4 minus 5. So let's just take these two. I'm missing out one in here, so I'm confused. Okay. What this provides you is properties over the individual variables that hold for all runs observed. Here, we do have a precondition, and this precondition, we see that A is always greater or equal to 0, and this actually holds for all the runs we have observed. So in the first call, A is greater or equal than 0, and then the second call, A is also greater than 0. And we also have the same property for B. B here is also always greater than 0, so that's fine. And we also have a postcondition that holds. And this postcondition is actually a function over the return value and A and B. So it's the return value as well as the two input variables. And our postcondition here is that the return value is greater or equal to 0. So now I'm actually seeing a bug in here, and I'm confused because we should also see another postcondition, namely that the sum of A and B actually is equal to the return value, and I'm just wondering why this doesn't come out here. But let's take a look into how this is actually achieved. So the way this invariant annotator works is that it actually, so we can look right into the actual implementation here. And the idea here is that you do have a set of properties. So let me just search for these. If this thing ever becomes reactive again, wonderful. Properties, isn't that set properties? 1 second, I'll be with you in no time. Yeah, that's all fine. We have our properties is somewhere down there. That's fine. Okay. 1 second. My computer is almost breaking down. So we go for uppercase here, such that we actually find things. Oops. Yeah. Things don't exactly work as expected here. Here we go. This is what we're having. Okay, and these properties which we see here are all placeholders that get instantiated with individual variables, and then they are being checked on whether they hold. So in our example, we have seen here A is greater or equal than 0, and B is greater or equal than 0. This is an instantiation of this invariant pattern. X is greater or equal to 0, except that X, the big X here, is being replaced by the variable in question. And what this invariant annotator does is it takes these patterns and checks which of these patterns actually apply to all runs of our function that we have observed. So in our case, X is less than 0. Does that hold for A or B as seen here? No, so it's dropped. Does X less or equal than 0 apply for any of the variables we see in here? Well, less or equal than 0 is true for this run, but it's not true for this other run. So this is dropped just as well. And we do have quite a number of these properties. So we do have X is less than 0, X is greater than 0. We have X is equal to Y, X is greater than Y, and so on. We also have we also do have types in here. So X is an instance of the Boolean type, X is an instance of the integer type, and likewise. And we also do have invariant properties such as relations between multiple variables. And also, well, this is a typical Python fashion, a greater or less relationships between 3 variables. And we also have Boolean, such as X or not X, which, by the way, also translate into a list being empty or a value being non-zero as it is in Python. And we also do have X is equal to the length of Y, or X is equal to the sum of Y. So if there are properties like these over collections or strings, these also will eventually show up. So, and actually, since all of these normally would all be checked and instantiated, and I had tried this out yesterday. I'm just confused why we do not see these in here. So let me just do a little check here. Otherwise, we'll go into a bit of debugging, which is a bit boring. Dynamic invariance dot invariant. Upsala. Invariant. What is it? Invariant properties. Yes, of course. So let's see whether everything is in here as expected. Dynamic invariance. Okay, good. Import dynamic invariance. Here we go. And this is very interesting. Okay. Oh, this is super cool. I just found a big bug in my own implementation. This is really cool because when we're importing these invariant properties, for some weird reason, these later things here do not get added to that. Now that's really interesting. So let me just see whether I can rephrase this. Invariant, if I rephrase this to a properties plus. Okay, so that doesn't matter. We can just restart things here. Okay. And let's see, I have a suspicion on what might be wrong in here. So let's see. Yes, 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 yes. Oh man, this is a stupid bug. Really, really. See. If you just write plus equals. So let me explain things here. So we're having a special importer here, which allows notebooks to import each other. But when we import things, we're having a special pattern such that we don't just rerun the entire notebook while importing it, which normally would be the case. That's not what we want. But instead, we're only importing cells that follow a particular pattern, and the cell pattern that we are looking at is either it is a definition of a function, or it is a definition of a class, or it is a global variable. And a global variable must follow the pattern, a name in uppercase letters followed by an equal sign. And plus equal is not it. And this is why the very example which I've just shown you wonderfully works when we are within this notebook, but not when we are importing things. So good I found that. Because otherwise you would have wondered, oh man, why can Professor Zeller do all these magical things in his notebook, and why can I not import all these things into my notebook? Yeah, what a pity. Okay, good. Let me just fix these things, and then we can actually look at the full set of notebooks. Here we go. 1 and 2 and 3. Okay, that was a quick fix. Oh, forget about override. So we override things wonderfully. We have things fixed. We restart things. See, this is live debugging, ladies and gentlemen. We are fixing things as we're fixing things right in the notebook while we're talking. And now we finally have all the properties that we're checking, and you see the whole list. And now that is when you actually see the full set of invariants. And okay, good. And that's actually, and now you see that there's quite a number of invariants that all hold for the runs that we've seen. So we see, for instance, always A is less or equal than B. And we also see that always A is greater or equal than 0. And interestingly enough, we also find that there's a postcondition. The return value is always A plus B, which actually is precisely the return value we want to see. And what we also have is we also have type checks in here. A is an instance of an integer, and B also is an instance of an integer. Okay, so the trouble with dynamic invariance is that we are limited to the incompleteness of dynamic analysis. That is, we can only look at what we have. And therefore, we do have quite a number of false over approximations in here, because, well, the fact that A is less or equal than B need not be the case, actually, for some two. There's no need to do. It just so happens that we had that in our very set of runs. So of course, as soon as I add another call where this is no longer the case, then this precondition magically and immediately disappears. And what we also can do is we can also add in some negative values just for the fun of it. And then we also get more preconditions that disappear. And now, because all these greater or equal than 0 or whatever disappears, and now we actually do have a set of invariant candidates that actually make more sense, because what we have now is the return value is A plus B, which is actually the post condition as it should be. We also do have that the return value and that A and that b are all instances of an integer, which is also how it should be. Well, it depends on how you want to define sum2, but if it's only used with integers, then that's what you get. And we also have these, a is the return value minus b, which of course is implied by the other postconditions as we have them over here. Now, if we go and invoke this also with, floating point numbers, just for the fun of it, then we will find that how the set of postconditions further is reduced. And now they have the one interesting postcondition, namely that the return value is equal to a plus b. Downside of the whole thing, you won't believe it, but this actually also holds for strings. So if I put in a plus b, then, oh, sorry, not a plus b, what am I saying? A and b, here we go. Then you will find that this postcondition return value is equal to a plus b still holds, because this is a postcondition that also holds for strings. The postconditions with b plus a, however, does no longer hold, because in strings, the plus operator is not commutative, and also the postconditions which we had previously with a minus, as we had them when we were only looking at numbers, here we have them again. These also no longer are there because, well, minus does not apply to strings, at least not in Python. Okay, but that's something we'd like to avoid here. And of course, well, let's stick with integers such that the invariant annotator also gives us pre and post conditions for inputs. And again, the way this works is by taking these patterns, and you can actually add more to these as you like, is to take these patterns and instantiating them every time with every call and every combination of variables, and retaining those instantiations of these patterns that hold for all runs observed. And this can then give you nice candidates for pre and post conditions, assuming, of course, that you do have sufficiently many tests. Now, how is this being used? In particular for debugging, but also for testing? Well, there's multiple uses of specifications. The first thing, and that's rather obvious, is you can throw this right away in an assertion checker of your choice, convert these preconditions and postconditions into checks. Actually, this is actually already being done here. These postconditions and preconditions are actually implemented. This is actually code, yes. These are actually implemented as function transformers, which add a check at the beginning and at the end of the function, checking whether they are satisfied. I think I can take this entire blob of code here and execute it. So if I do this, can I do this? Oh no, I don't have precondition and postcondition. So what I need to do is I need to import these first. So let me just see whether this works. So from precondition and postcondition. Here we go. And now if I execute this, now something magical will have happened. These precondition annotations here will have automatically modified the definition of sum2 such that there would be automatic checks being applied whether all of these preconditions and postconditions actually hold. And if I now invoke sum2 with well, things that do not match these learned preconditions and learned postconditions, then I'm going to get an assertion error. The precondition is violated because A is not an instance of the integer class, the integer type. Likewise, if I modify sum2 to do something different, say no longer adding things, but actually multiplying things, now I put in here, well, one and one would be, one and one actually works, because if I now invoke 1 and 1, and then it will automatically determine, well, this is a blob of things, it will automatically tell you I just violated the previously learned post condition, namely that the return value should be a plus b, and ladies and gentlemen, 1 times 1 is, as we all know, is 1, and certainly not 2. So let's fix things back here. So convenient, automatically gives you assertions, and these assertions can then catch errors. This can be helpful. I mean, this can be helpful, especially when you're having a change to your code. So you're taking the old version of your code, you're putting in these additional assertions, and then you take the new version of your code, the one that fails, let these assertions run, and you will immediately find out where things are different and violate what we have seen before. The second big usage of such learned, pre, and post conditions, and actually also type annotations as we have seen them before, is for formal verification. For formal verification, you need to know what individual types are, that's obvious, but you also need to know what a precondition is in order to formally verify that a post condition holds. So again, pre and post conditions are super important for that. And these also serve as documentation, by the way, for your program, because, well, it also in addition to types, they tell you what is expected from your function. So that's also very useful. And finally, and you will see examples to that in the chapter, you can also use them to find out which under which conditions something specific happens. So you take only failing runs of your function, and then you find out what are the pre and post conditions that apply in these failing runs, and maybe why are these conditions different from what I have in passing runs. This can also be super interesting. So this builds a nice bridge between dynamic executions and static checking, or runtime or continuous runtime checking, or also static analysis of your program, or symbolic verification. But let's not forget, there's also limits to the whole thing. And the obvious limit is that you do have a finite set of properties to check. So of course, these are important properties, knowing about the range of individual variables, knowing about plus, minus, basic arithmetic functions, basic relations. This is all neat, okay? But if you have a function that fails, if you have a function that fails on a full moon, for instance, okay? Well, the full moon, what is a full moon? You have a function that fails on Easter, and then you would actually need a formula in here that says, is Easter of X, or has some particular property of X, or anything related to date, time, whatsoever. All the specific domains in which your program might operate that go beyond these generic domains that we see in here, none of this would be covered. And indeed, you would have to go and extend your vocabulary of properties towards the specific domain in which your program is acting. And by the way, this is one of my all-time favorites. When I am saying that, oops, what happened to my A plus B here? When I am saying a program that only fails on a full moon, this, ladies and gentlemen, actually has happened. This actually, and it actually was different. This was a payroll, an employee payroll function that failed on all days except for Wednesdays. So when you ran it on a Wednesday, it worked, and if you ran it on any other day of the week, it would fail. Now, why would something fail only on a Wednesday? Well, it's very simple if you think about it. What happened was there was a string in the program which would actually take the number of days, okay? So that would be Friday, or Sunday, or Saturday, okay? So not too complex, right? So these are things which we would have. And now the interesting thing would be that Wednesday has a particular property, as you can easily see in here. it is actually the only day in the week that has 9 characters. And what happened was that the day of the week was stored in a field which only had 8 characters. So there would be an overflow from the field in which the week of day was stored, this 8-character field, into the next field. And this next field in memory of the program happened to be a Boolean value. And this Boolean value was normally actually also erroneously initialized to N for no. However, when on a Wednesday, this magical field would be overwritten and become a Y for yes. And only if this field was set to yes, which was another error. So this first error, this buffer overflow error would cancel out the other error, namely of this other Boolean flag here being erroneously set to N for no. And only then would the payroll actually be printed. So you can already see how the property of particular variables can affect the outcome of a program. And if you extend the set of if you go and extend the set of properties towards something that says, let's say, length of x is greater than length of y. Here we go. Or actually greater or equal, doesn't matter. As soon as you have such a pattern in your set of invariant properties, then this property may be instantiated as length of Wednesday is greater than the length of the day of week. Or actually, the way it would really look like is input day of week. So this is the string that would be input, and this is the string which would be used to store it. And this, ladies and gentlemen, is a property that would hold only on Wednesdays. And if you now mine those invariants for those runs that pass and those runs that fail, then you would find out that on runs that pass, then this property would hold, and on runs that fail, this other property would hold, giving you an important hint on why the program failed. Now, this is mining invariants, and this is actually just a short, well, a small fraction of what actual dynamic invariant miners can do. The mother of all dynamic invariant miners is the so-called DICON tool by Michael Ernst and colleagues, in particular, Bill Griswold, David Notkin, but the true genius came from Mike Ernst here in this case. And he was the first person ever to actually come up with such patterns and see whether they can be instantiated and see whether they hold. And his work on DICON has been shown to be highly influential in the field. Is one of the most frequently cited papers in debugging. It's one of the classics in the field. And with the implementation which we have here, this has far fewer features than DICON. DICON is far more sophisticated than that. But on the other hand, it allows you to experiment with this on your own. And this is precisely what I'd like to invite you to have a look at the implementation, have a look at possible usages, and try out how dynamic invariants can help you figuring out what a particular piece of code is doing and what the weaknesses are, but also what the strengths are. With that, I'm happy to have concluded today's lecture. Now with a real bug. Finally, I always have been waiting for this. I have had a real bug in a lecture, and I've been able to fix it right away. Oh, I'm a genius. I should become a professor of sorts. Oh no, that's probably not what I should do. Maybe I should work harder on creating code that actually works. Well, this will now be fixed, and from now on you won't have any trouble with that. Okay, That's all for now. Thank you very much for your attention, and have fun with invariants. And I'm happy to take questions if there are any questions, that is. So let me see. I have a Q&A window, no open questions. I do have a chat window. I have no open questions here either. Konstantin, do you have any questions?
Oh, not really. I like the story much. So maybe one question. How easy is it to use, and how beneficial is it to use this approach in production?
Well, in production, Dicon helps in providing important invariants. So simply knowing that a value is always greater or equal than 0, or knowing for C programs, for instance, that an integer that you pass is equal, that this is actually equal to the length of the string that you're also passing, or you're sorting something and you're passing the number of elements to be sorted. All of these can be important hints. The crucial part in the whole thing is indeed the set of runs that you observe, because if this set of runs is not representative for actual use, then your invariance will be either too general or too specific. And this is why people also have been trying to combine the Dicon invariant detector with test generators. But then the trouble is, and that's actually bad trouble, if a test generator sees a definition like this, okay, here comes some 2. The test generator doesn't know either whether you have to put in strings in here, or whether you have to put in numbers in here, or whether this is actually meant to take whatever thingy, a complex number, a class of my own, anything for which the plus operator might be defined, okay? So you're having a chicken and egg problem here in this particular setting. You have a test generator. The test generator doesn't know what goes in there, and so it can put anything in there, and then the dynamic invariant generator can learn anything from that. And this is a chicken and egg problem, which is difficult to resolve. The best way to resolve this is by having a good test generator at the system level, where system inputs are being produced. And because there the program is supposed to reject any inputs that are syntactically or semantically incorrect. And this is then how we can then learn indeed proper invariance for all the executions. But then again, you need a system test generator that happily covers all conditions, all branches, all situations. And this is still subject to further research, as being done at our chair, for instance.
And I have another question, probably a follow-up question.
Yes.
So how to come up with the good set of invariant properties?
Well, if only one knew. So the basic thingies, as we have them in here, this is just a small set, say types, arithmetics, and everything. This is probably important. But the really troubling question is, if you have a program in a particular domain that in which you have properties that are important, but how do you extract these properties from your program? How do you get these out? And if you do have say some image manipulation program, the property you may be looking at is some particular value of pixel sets, sometimes distributed across multiple sets. You don't know, or even make it even harder. You have some artificial intelligence, some image recognition program. Here's an image recognition program. Here's your favorite neural network trained on flower images. Okay, good. And sometimes it classifies something as a flower, and sometimes it doesn't. Great. Now try to characterize this as a formal invariant. Okay, you have the choice. Either you look at if this pixel has this color, or this pixel has that color, or this pixel has maybe that color, and this pixel does not have that color, which doesn't make too much sense. Or, that's number one, or your dynamic invariant generator gives you an abstraction that tells you the program recognizes something as a flower whenever the function isFlower returns true, which is not easy either, okay? But then the question is, what would the perfect explanation look like? The whole point of machine learning systems is that they can do things even in situations where we cannot provide a specific formal and very clear distinction between two sets. And this is where we are at the limits of things that we can explain and things that we see. We make decisions without being able to explain them. And even in retrospective, looking at all these decisions is not always easy to provide such an explanation.
And are there any systems which are not possible to use with this? Well, for which the dynamic invariants make no sense at all?
Well, as I said, if you have, say, if you have a trained classifier, for instance, what on earth could an invariant detector tell you? It could tell you this neuron has this value, this other neuron has this value. Doesn't make any sense.
Well, for a low-level code, it may make sense to catch some minor bugs.
Yep. It can work for low-level code, can also work for high-level code, assuming that there are properties that one can encode in these invariant properties. It can also be, you can also think, say, you're modeling a university, and then you have professors, and you have lecturers, and you have PhD students, and these have specific properties. Then you can also find out that, say, the precondition for a lecture is that there be at least one lecturer and 0 or more students. These are also things that you can find out this way. So it works at high level, at high application level at a model, as also as at low level. I think the main thing to look at is whether there is a model that can be easily learned. So if there's a chance for a model that can be crisply defined, then there's a good chance for an invariant learner like this one to actually come up with good candidates for things. Does that answer your questions, Konstantin?
Yes, thank you very much.
Okay, maybe we should apply this to find out under which conditions an Android application has a defective user interface or not. Maybe there's misuses of specific APIs, and likewise. Well, if you apply this to APIs, for instance, you can learn how people typically use APIs, and then you can retrofit a specification on it. I mean, you can also use this to find out about states and transitions and everything. Plenty of opportunities in here, but also long-standing limitations. This is room for research and experimentation. Okay, no further other open questions.
One of our students will be interested.
I guess our students will be most interested in getting the results of getting out the results of their first project, and as well as the next project description, which we can only send out after all our recording here is done. So without further ado, it was a pleasure. Let me close things today, and we'll see each other next week. And in next week, we will either come up with debugging in the large, which is handling of bug reports, and more interesting, mining version databases and bug databases to find out where in a program the most bugs are. And as you have seen, there will be now one more bug to be fixed. So we know that dynamic invariance has one more bug. That's either we're going to look into that, or we're going to look into how to automatically abstract and capture the conditions under which a program fails using a nice combination of, again, invariant learning, and but then combined with automatic feedback. So either it's first this and then the other one, or first the other one and then the other, or yeah. Well, so the next two are set. It's just a matter of which one gets ready first. Okay, let's close things here. Thank you very much for attention, and see all of you next week, and have fun with the new project. Thank you. Bye bye.